Mr. Gagnon again, you might want to adjust your settings where you're looking at 1.25 speed on YouTube. This is going to be your first section of math of kinetic frictional force, and we'll look at a little bit of static frictional force here. So I'm going to shoot you guys up with a formula. Force of friction kinetic, okay, is equivalent to, and don't get confused by the terminology here, we're going to look at it a little bit more in depth and make it easier to understand. Now there's this weird little symbol called mu, okay, and I'm going to call it mu k, mu sub k. Okay, now when I was back in high school, I had a physics teacher that wrote this a little differently, and I'll write it up. I'll write it down here so you can see it. Now this is how we're going to write the formula. The force of friction is equivalent to mu k times, so you might even want to actually draw like multiplication symbol there, times the normal force. Now I had a physics teacher that you may like this, may not like this, but I had a physics teacher who wrote this as, and don't write this bottom part down, F equals mu, and he called the normal force just N. And he used to try to make us laugh. None of us did, and none of you probably will, but he used to say physics is F-U-N. Physics is fun. And this actually was a good memorization tool to memorizing this formula if you had to. Back in the day, I had to memorize formulas. You guys don't. You have a note card. Okay, so that was what my physics teacher used to call it. Now, if I have an object like this, like a box, sitting on a surface, I'm going to say the box weighs has a mass of 2 kilograms. Okay, and I want to know what kind of frictional force is going to be pulling back. Now, what I'm going to do is I'm going to draw a string pulling this way, and I'm going to apply 20 newtons of force to this. Now, here's the deal. You want to start getting into the habit of writing all 4 forces. Okay, this is the applied force, Fa. Okay, we know that there's going to be a frictional force. And guys, if this is moving, then the frictional force is going to be the kinetic frictional force. Okay, we know also that we're going to have a weight. And then we also know we're going to have a normal force. Now, we're going to go through this whole problem. I'm going to help you guys calculate some numbers here. All right, and the weight is equal to, remember, mass times gravity, 2 times negative 9.8 Okay, so now don't forget to convert mass to weight, FW. Okay, so what this thing weighs is negative 19.6 newtons. Now we know that this is equal to this because these two are balanced. So the normal force is equivalent to the opposite of this. So 19.6 newtons, straight up. So I got the weight, I got the normal force, 19.6, and they want us to be able to find this frictional force. Now, I haven't told you what this mu value is. Okay, all this is, okay, this mu value is a number that changes with surface type. Okay, and so on excuse excuse me, on page 109 of the notes, there's a chart that tells you the mu value, we call it, and I'll actually spell that out for you. M-E-W. Okay, I know you can't see that. I'm gonna bring this up a little bit. The mu value is this, and that number changes with the surface type. So if I go onto my chart and I find out that this block is a piece of wood and this block is a piece of wood, then wood on wood is equivalent to 0.2. Okay, so if this is wood and this is wood, then I've got a mu value of 0.2. No units there. So if it were ice on ice, it would be a lot less. If it were lubricated metal on lubricated metal, it'd be a lot less. But we're going to look at wood on wood, okay, and then we're going to look at the formula. The force of friction kinetic is equivalent to mu kinetic times the normal force. So look back at our normal force. We've got a mu value of 0.2. We've got a normal force of 19.6 newtons. Okay? So I'm very easily able to calculate the frictional force by multiplying 0.2 times 19.6. Okay, I ended up getting 3.9 newtons. So look at what we have here. Now this problem's getting a little bit more challenging now because I've got a lot of working parts here. I've got a frictional force. Okay, we ended up saying that this was 3.92. Let's actually call it 3.9 newtons. Okay, now we know that's acting in the negative direction. So the question I have for you then is, yes, you were able to calculate that frictional force. I know the applied force. I know that these two balance. They cancel each other out. So my question to you is, what is the net force of this whole system? And you should say, hey, well, 19.6 cancels with the 19.6. Those are gone. I got a 20 pulling to the right. I've got a 3.9 pulling to the left. Okay, so my net force on this entire system, okay, is 20 minus 3.9. 16.1. Now I've gone a little further with this video and I'll explain more in the next, but I've found the net force acting on this block because of its friction now is not 20, but it's 16.1. I'm going to take it to the next step. Again, this is a long-winded video, but I'm going to take it to the next step and say, hey, you know, what's the acceleration of the block? First of all, guys, we know that it's going to accelerate to the right because the applied force is bigger than the frictional force. So, acceleration is net force over mass. We know our net force is 16.1. Our mass, we said, was 2 kilograms. Okay, so we're able to actually calculate the acceleration of this block as 16.1 divided by 2. So the acceleration is 8.1 meters per second squared to the right. So we're able to actually fully solve an entire problem. Again, I'm going to do a couple more on the next videos. I decided to take this full on and get it all done for you. You may want to replay this one because there is a lot involved here.